All right, in this video, we're going to start off chapter 8. The first thing that we're going to take a look at is something called geometric mean. So before we get into that, there are a couple of algebraic properties you need to remember from last year or the year before. These are properties of radicals. So from here on out, we're always going to write our radicals in reduced form, meaning none of the numbers inside of our radical will have a factor that's a perfect square, like 25, that's 5 squared, or 16, that's 4 squared. None of our square roots will have any of those numbers as factors. So we're basically going to reduce them and take their square roots. To do that, we're going to use these two properties. The first one says that if you have a square root of two numbers multiplying, then you can break that down into the square root of each factor. And then the second property says basically the same thing, but for division. If you have two numbers dividing in a square root, you can take the ratio or the fraction of the square root of your numerator divided by square root of your denominator. So we're going to use those a whole lot throughout the rest of the semester. So to start off the geometry part of this, we're going to look at what is geometric mean. So if you have two numbers, let's say A and B, and they have to actually be positive. This doesn't work for negative numbers. The geometric mean is defined as the square root of the product, kind of like that thing we saw just a second ago. So you multiply them together and take their square root. So for example, let's say I have some pairs of numbers, 2 and 8, 25 and 3, and I had to find the geometric mean. Well, for the first pair, I take the square root of 2 times 8. That happens to be 16, and the square root of 16 is a 4. So that's the geometric mean of 2 and 8. For 25 and 3, multiply those together under a square root. However, we can use that one property that a product in a square root can be broken down into a product of square roots. The reason why you want to do that is because we know the square root of 25 is actually a 5. So we'll rewrite that as square root 25 times square root 3. We know the square root of 25 is a 5, and so 5 square root 3 is the reduced form of the geometric mean of 25 and 3. How does this relate to what we've been talking about? Well, it has something to do with similar triangles. So supposing we have a right triangle, triangle XYZ, and we draw an altitude to the hypotenuse. So that red segment YW is an altitude of right triangle XYZ. Turns out there are 4 things true if you have this scenario. First off, using angle, you can actually verify that triangle XYW is similar to YWZ, which is also similar to XZY. Using those similar triangles, you can write out a whole bunch of proportions like we saw in chapter 7. And with those proportions, you can actually come up with formulas for the altitude YW and the legs YX and YZ in terms of the other parts. So the first one has to do with the altitude. So YW is actually the square root of XW and WZ. Those are the two parts that make the hypotenuse of your big right triangle. This should look pretty familiar. Another way to say this is that your altitude length is the geometric mean of the two lengths of your hypotenuse where that altitude meets the hypotenuse. So that's our first formula for the altitude. The second formula we have is for a leg. So leg XY in yellow, that is the product under a square root, i.e. geometric mean, of XW and XZ. So these two formulas are very similar. The difference is that the geometric mean on the second one has the entire hypotenuse, XZ, whereas the altitude has just individual pieces of the hypotenuse. And we've got one more formula for the orange leg, YZ. So pause this video, see if you can guess what it is. All right, so if you guess this, then you're correct. It's essentially the same as that formula right above, except you use a different part of your hypotenuse. So you're going to use WZ times the entire hypotenuse under that square root. So these are formulas for each leg and the altitude of a right triangle. When you have that altitude drawn to the hypotenuse, each of them is a geometric mean. It's the square root of a product.